Now let's see how we can perform a limit point analysis to obtain the buckling load of a structure. Now we discussed the bifurcation buckling, but the disadvantage of the bifurcation buckling analysis, at the end of the day, we just get a scale factor. And this scale factor applies to the whole loading that is existing in this structure. But sometimes we may want to check, you have certain loading on the structure, and you want to check excite certain mode of buckling with some sort of a loading, and you want to check under these single load will your structure buckle or not. So for this purpose we perform a limit point analysis, and what we are doing in this analysis is we are doing a nonlinear static analysis and incremental nonlinear static analysis, and we are searching for a limit point. So when you reach a limit point, it means that your stiffness matrix, the whole stiffness matrix, becomes singular, and singularity means the system structure becomes unstable, and which we say that it's the buckling point. Okay, so let's write that. The buckling load of a structure can be determined by tracing full load deflection path of a structure. And this can be done by performing incremental geometric nonlinear analysis. Okay, so how do we do it? Again, let's take a look at the column example. So we have a column here, and we have P. Now, in order to perform a geometric nonlinear analysis, I have to give a small perturbation, small deformation to the structure. Now, I know that this structure, the buckling mode of this structure will be something like this. So in order to do that, generate this type of a deformed shape, I apply a small perturbation load. Okay, this could be a very small load, okay? So this is the perturbation load, and this load will generate a lateral displacement, let's call it delta. And this is the displacement that we are going to trace. So in this analysis, I will incrementally increase the axial load. This one remains the same. And I will check what will happen if how this delta changes if I incrementally increase delta. So at the end of the day, this is what we usually see. Remember that in the bifurcation buckling analysis, this is what we are looking for. And then we reach to P critical, and then it goes this way. This is the bifurcation buckling analysis. Now, in the limit point analysis, we do incremental loading, and we are checking the variation of delta with respect to P and then we usually see a behavior like this, and when you reach to the P critical, your displacements diverge. Okay, and at some point you reach a limit point, and this is the result of the limit point analysis. So the advantage of this, you can only incrementally increase a particular load, a single load, and check the deformations, whether they increase, whether they remain stable or not. But the main problem with this is when you have a structure like this, it's easy to guess how it will buckle. But when you have a more complicated structure, you don't know how the structure will buckle, and you don't know what type of a perturbation load that you should define. So usually what we do is we first perform a buckling load and then get the mode shapes, and then use this mode shapes, define a perturbation load, and perform a limit point analysis. Now let's take a look at how we can perform a limit point analysis. Again, this is the same code that we discussed before. Now, instead of doing the bifurcation analysis, I'll use the same code to perform a limit point analysis. As we discussed, limit point analysis is nothing but an incremental geometric nonlinear analysis. So for this, I implemented two methods. One of them is the Newton-Raphson method. So here, this is how it goes. Now we have, this is the incremental part, and here we have the iterations. For the increments, again, we first solve and determine the structural stiffness matrix. So this is the, remember, that's the flag. Flag gives me the elastic stiffness, and then I'm performing this linear solution and obtain the displacement increments, and then the iterations start, and at every beginning of the iterations I calculate the axial load, and from that, by using that axial load, I'm obtaining the resultant forces. Okay, the resultant force, let's again go back and take a look at the resultant force calculation. Here it is. So in the resultant force calculation, I'm calculating the geometrically nonlinear stiffness matrix, in other words, K plus Kg or K plus K sigma, and then multiply it with the global displacements and obtain the global forces, and finally assemble it to the force vector. And let's go back to the algorithm one more time. So here I'm with the current displacement, calculate the axial forces on every member, and then get the force resultants, and from that calculate the residual force. If the residual force is smaller than our error value, then it stops. Otherwise, it updates the stiffness matrix, again K plus K sigma here, update the stiffness matrix using the P, calculate displacement increments, add it to the total displacements, and continue this iteration until you obtain the convergence. So here the nonlinearity only comes from the structural geometric stiffness matrix. So this is the Newton-Raphson iteration. So we also use the ArcLength method to solve that. This is we discussed the single degree of freedom version of it. Now let's take a look at the multi-degree of freedom version of it. This part doesn't change because it's just the solution of a quadratic equation. Now we have the choose solution part. Now remember that for a single degree of freedom system, this is what we were doing. We were just multiplying it. But here we just multiply the transpose. This is a vector transpose multiplied with another vector gives me another scalar vector. Instead of p square, we have p transpose times p. So again, we are calculating the projections. So the only difference is, instead of a scalar multiplication, we have the vector multiplications here. But the rest remains the same. Now the ArcLength method, this is the main algorithm for it. So the increments, remember that increments are determined by this arc length, and we have this phi here. Depending on the value of phi, we either have a spherical arc length or a cylindrical arc length. So we start, we form, this is our predictor solution. We calculate the stiffness matrix. Again, I am using 3 here. This is K plus K sigma. And then do the solution, get our first displacements, use the total force here. And then with this region, I'm scaling up so that the length of the first increment will be equal to delta L. This is what we do here, solve for lambda. We were looking at the sign of the stiffness matrix. Here I'm looking at the sign of the determinant of the stiffness matrix of KT here. And if the sign of the solution and the sign of the determinant is the same, we choose the first solution. Otherwise, we chose the second solution. So these parts are again the same. So instead of adding the scalar, I'm just adding the vectors here to determine the total displacement and the scale factor. This is still a scalar quantity. So this part again the same. Calculate the axial force by using the total displacements. From that, determine the residual force, Fe, and the external force is the total scale factor times the force vector, and subtract it from each other, get the residual force. Okay, if you have your residual force is larger than your error limit, continue the iterations, get your new stiffness matrix, get your UP hat. Here you just use the residual force, and then we have the UP total. We use the total force here and calculate A1, A2 and A3 coefficients. And as you see, instead of scalar multiplications, we have the vector multiplications here. And after those vector multiplications, I obtain these 3 scalar factors, and using that determine your incremental load factor, choose the correct solution here and update your quantities. Now let's work on an example problem. Again, the same problem. We have this cantilever, and we already solved this by using these 2 analytical solution, and this is the bifurcation buckling analysis result. So we expect to see buckling around 1300 kilonewtons. Now I'm performing a limit point analysis, the first with the Newton-Raphson method. So I'm applying a load that's equal to 1370. Okay, and the way I load the structure is as follows. If we draw the figure here, this is the cantilever we have. So I'm applying an axial load that's equal to 1370, and a perturbation load delta F will be equal to 1. Okay, so this is my perturbation load, and I'm tracing the load deformation curve, this load versus that displacement. So the x-axis is the displacement. So I'm solving this by using 10 increments. So as you see at the beginning, the delta is small, it doesn't increase, but as I increase the axial load, the deflection starts to increase, and when you get very close to the buckling load, you see a very huge displacement. So somewhere here you have the limit point, and after that you can continue. You will see that after that your solution will be ridiculous. So this is the result with the Newton-Raphson method. Now let's take a look at the ArcLength method. Now one thing that I want to mention here is look at the magnitudes of the displacement and the magnitudes of the forces. And our arc length definition, if you go back, is right here. Right? This is the way we define the arc length. Is phi is equal to 0. So the arc length will depend only on the displacements the vector norm of displacements. We can think of it that way. So if I make phi is equal to 1, then the forces. If the displacements, magnitude of the displacements are close to the forces, then we will see a combination of it. But in this example problem, or in this, the way I solve it with the units, the magnitudes of the forces are much larger than the displacement. So that's why I used, in the arc length solution, I used phi as equal to 1. And delta L represents actually my force increment. Okay, so I'm just increasing the force by 69 kilonewtons, and I'm applying 20 increments for this specific case. And as you see, I got 20 increments. We go with 20 increments, and as we approach to the buckling load, again we see a huge displacement between these increments, and that's where we have the limit point. And this 69 times 20, which is very close to this value, gives us the buckling load. I don't have to know it, but once you start solving it with the arc length, again after that point you will see negative behavior, because remember that this is a single cantilever. If you exceed the buckling load, you lose the stability, and you don't have any other additional path or post-buckling stage to catch up the stability one more time. So if it loses, then your structure will fail, completely fail, because you have a determinate system. So that's how it goes. And again, with the cylindrical arc length method, we were able to determine the buckling load. Now let's work on the second example. Remember that this is a frame now. Let me draw it one more time. I have this frame. So we did a bifurcation buckling analysis, and the bifurcation buckling analysis gives us our buckling load as 3,137 kilonewtons. And remember that I have -1 and -1 here. If you multiply this scale factor with these forces, you get your buckling load. So in the bifurcation buckling analysis, remember that this scale factor applies to all the loading that you have on the structure. Now in the limit point analysis, what I did is this. So again, let's draw the frame one more time. So I apply axial loads that's equal to 3100 to the top of the columns, and then I apply unit perturbation load that's equal to 1, and then trace the variation of the displacement of this frame, that displacement with respect to the magnitude of this axial load. So again, we start with the Newton-Raphson method. Again, I use 10 increments, and as you see, very close to this number, we see a huge displacement in the lateral deflection, which tells us that it's lost most of its lateral load carrying capacity. The column and the full structure buckled. Again, as expected with the cylindrical arc length method, the result is no different. So I'm using an arc length method, a cylindrical arc length method again. And as you see, as the P reaches to 3100, the structure fails. Remember, here I'm using 4400 as my arc length, the final arc length. I define the arc length as 220, and I use 20 increments. Remember that I got two loading, right, 3100 and 3100, and we are looking at their vector norms. And if you just calculate, I got two forces and square of it multiplied by 2 and take the square root of it. So this is the total arc length when I see the buckling load. And magnitude wise, if you just come here and see it again buckled around 3100. So the main disadvantage of the bifurcation buckling analysis, let's repeat, we at the end of the analysis we obtain a single scale factor. Okay, so this is our scale factor here. So what it tells us is, whatever, I may have very different loading on this structure, okay, very different types of loading, and I want to look at the buckling, and it gives me a number. This is a scale factor. How to use it? There's no direct way of using it if you have a very complicated loading like this. So what we usually do is, we have a structure like this, we under certain type of loading, we perform bifurcation buckling out, and we look at the magnitude of this, the critical loads. So if the magnitude is very small, right, 1, 2, 3, you say that this structure is very critical to buckling. So the stability is at the risk, because remember that I'm solving this as a perfect straight elements, right? All the loads are applied to the centroids and lots of assumptions here. Everything is elastic, no residual forces and so on. So that's why if I get a large number here, I know that, okay, stability wise, the second order effect is not very important in this structure. Now, what will happen if you think that this the geometric nonlinearity or the stability is very at the critical point? Then you look at the mode shapes, right? The buckled shape. So the buckled shape probably will give you this. And then you perform a limit point analysis, as I did here. You put all your loadings, whatever you have on the structure, okay? And then give a perturbation load, and then start doing incrementally increase the loads, okay? You can just first load it with the current loading and just incrementally increase a certain load. That's possible in this type of analysis, okay? You keep increasing the load and see where it goes. And try to figure out if you reach a limit point or not. If after a certain level of load, if you don't reach any limit point, you will say that, or the softening is not that significant, you will say that, okay, the stability in the structure is not an issue. But if you face a problem like this at loads very close to your design load, then you may want to change the design of it. So from this, we will check whether the critical P is large, or in other words, we say that, okay, is this, in terms of stability, is this a critical structure? Okay. If you get small numbers here, 1, 2, 3, it means that yes, it's a critical structure. Then we perform a more detailed analysis, and the advantage of this analysis, under the given loading, you obtain the eigenvectors. That gives you the buckling modes, okay, the weakest deformed shape that may cause buckling. And then in the limit point analysis, you adjust your perturbation loads in such a way that they will generate that deformed shape, and keep increasing these perturbation loads and see if you really reach a limit point or not.